Miss Jody here with another video for chemistry, which meets on, when does it meet? Monday afternoons from 1 to 3:30. And we are closing in on finishing our chapters. Actually, I went ahead and did all of module 15 to make this the last video for our class. The book does go up to 16 modules, but as always, we don't always finish every single one. And this class is dragging on a little bit because I was doing 2 weeks of module and we were already behind. So I know you're getting antsy about being done, and I know these videos are not of the highest quality when it comes to like our normal teaching time with hands-on instruction and being able to go back and forth and anything that doesn't make sense, being able to take our time with it. So we're very limited in what we can do with this online platform. And it's pretty sad because I miss you guys and I wish we could be together and we could have finished this out strong. But of course, the regulations are still in place for us not to be together. And today was supposed to be the announcement of when we'd be able to start meeting again and whether we'd be able to have summer camps. And they've delayed that announcement. Today they said they decided they weren't going to make that decision yet, so that's going to delay us even more. But I'm still hopeful at some point that we could get back together. I am going to be gluing in blank scientific method forms and sheets in our journal for small little reactions like the catalyst experiment I sent you last week, and not that crazy one because we know with our class that that probably could turn out pretty bad because we've had a few things, what shall we call them, interesting outcomes of our experiments. So I don't know if we would do that one. That really sped up the reaction and it was kind of crazy. But some catalyst reactions I thought we could do that aren't as explosive. So I'm going to put in some of the lab sheets. So if we do get together, even if we could do 1 or 2 experiments, that would be fun. And if they don't let us get back together and it goes too far into summer, well, then at least you'll have them in your journal. And if you did any experiments at home, you could fill that data in. So with this chapter 15, like I said, this will be my last video for this class. And then you can do chapter 16 on your own. And chapter 16 is kind of complicated anyway, oxidation and reduction and such. And if you're at the point where you are just done with chemistry and do not want to do it anymore, that is a tough chapter. So you and your family can decide how you want to finish that one. All right, but we are going to do chemical equilibrium so that we can get this kind of encompassing idea between equilibrium for the reactions that we've studied so far. Okay, so with that, let's get some of the basics down with chemical equilibrium. So what's happening is we have changes occurring in our reaction world all around us. There's always changing, physical, chemical side of changing, but the changes that occur constantly, but some changes are not permanent. So that means that there's a going back and forth between things many times in our changing world. We don't always realize it. They give the example of water freezing and then melting. Of course, that's a physical change, but the idea that it doesn't always stay a solid. When energy is added, then it melts to a liquid. And so there's always this constant changing in our world, right? So when we look at that with our formulas, when we normally look in chemistry, we write out our chemical reactions. And we normally write them as reactants coming together and forming products, right? So up until this point, that's how we look at reactions. You know, you've got these reactants, you put them together and they form the products. We've talked about things like decomposition reactions where you take something and then it decomposes back into its original constituent substances or elements. And but most of the time we visualize reactions as being one way, as if they couldn't go back the other way, and that as if the reaction, once it's done, once the reactants react and form the products, that it's over. But here's the thing. In reality, these products, the NO in its gas form, and specifically in this equation, we've got the NO2 in its gas form reacting with the carbon monoxide in its gas form, and then creating the NO in its gas form and the carbon dioxide in its gas form. But in reality, these guys, the NO in its gas form and the carbon dioxide in its gas form, will eventually collide and then in turn back into these particular two, which were the original reactants. So what happens is, the truth of the matter is, reactions go both ways. And so if you ever seen this little symbol here, and you probably saw that before and didn't really understand what was going on, because in other chemistry writings you might see that. But in our book, it's building up to getting us to understand the basic one-way side of things, and then now filling us in the fact that it's not always one way. Many times it's the both ways, back and forth. Well, basically all reactions have this back and forth side of things. Now, there does come a point when the back and forth between these two, even though it's still going on, it gets to the point we call chemical equilibrium. And that's kind of the balance point among the reaction, where the forward reaction, so if we take this reaction, we would say, okay, we start with these two products. They begin to react. At this time, no products are formed. So the only thing you have is the forward reaction, because these haven't formed yet. So they begin to react and start to form the products. Then once the products are formed, when it meets at a certain point, then there would be a possible reverse reaction when they collide and turn back into each other, like I just said in this situation. So this first part, as it's beginning, we would call that the forward reaction. But then eventually, once products were there, and products could collide and turn back, we would call that the reverse reaction, the bottom part of the arrow. So the first part of this arrow would be the forward reaction. The bottom part would be the reverse reaction. Now, when the chemical reaction reaches this point where you have the forward reaction and then now the reverse reaction, and it's kind of in this balance point, we would call that chemical equilibrium. The point at which the forward and reverse reactions in a chemical reaction have equal reaction rates, meaning at first, we would have this forward reaction would have a really high rate. Remember last chapter we talked about the rates of reactions when we were talking about things going faster or slower and how we could speed them up. So at first, this one's going to have the fastest or the highest reaction rate because the products haven't even formed yet. So this one obviously has a higher reaction rate. But then over time, as it reacts and forms the products and they begin to get in that balanced position, then the forward reaction rate could balance out the reverse reaction rate, the rate at which these guys want to keep trying to go back to this point as they go back and forth, and that's what we would call chemical equilibrium. Okay, so they would both have this equal reaction rates. Nobody would be faster than the other, and it would balance itself out. Now, a few things to note about this. The amounts of each substance in the reaction will not change despite both reactions still proceeding. So what that means is that the substance is like, if I have a certain amount of this substance and a certain amount of this substance, and it forms, these two come together and form these guys, that's a certain amount of carbon dioxide, a certain amount of NO, right? So, but as they're going back and forth, it's saying the amounts of each substance in the reaction will not change, despite the back and forth side of things, the reaction's still proceeding. And that makes sense because once you get to that chemical equilibrium, just think of it as like a back and forth teeter-totter sort of thing, where at one point you were really leaned on one direction, but then when you got to the other side, like say you stand on a teeter-totter, you're all on one side, but then you keep slowly inching yourself towards the middle. There comes a point when you can balance back and forth with one leg on each side of the teeter-totter and create that balance, that equilibrium. And so your amount of you is not really going to change as you balance back and forth, because when you lean on one side, let's say you lean on your left leg, then it makes you want to, it starts to go down, you lean on the other leg. And then you lean on that leg back and forth to keep trying to get it to be balanced. And so this is illustrated in this diagram here, which is charting. Now this is better, of course, in your book, and always look to your book for better illustrations than my little doodaddies here. Again, this is just for taking notes so we can glue them in the journal. And so this little diagram I colored them. So this is the amount of time, and this is the reaction rate, okay? So lower reaction rate, I didn't put any numbers there, but lower and then higher reaction rate. So I start my reaction here, and I have the forward reaction, the first set of the reaction. It's got a high reaction rate because it's starting to react together. None of the products have been formed, so this side of it going this direction can't have a high reaction rate because it hasn't even started yet. So these guys get started and you have this really high reaction rate, but slowly over time, the more that the products are formed, then it gives the opportunity for the product side, which started out really, really low because the products weren't even there. So of course the products, if they're not even there, you definitely don't have a reaction rate. You can't send the reaction back this way with the second arrow if it's not even formed. But then the more that the products form, then the higher the reaction rate over time. And so eventually the forward reaction meets at a certain point with the same reaction rate as the reverse reaction eventually gets there. And when they both get to this point, then the line of the reaction, the chemical or the reaction rate between both of them plateaus or evens out here. And that's what we would call the chemical equilibrium. Now, once it's there, the reaction will stay at equilibrium forever, unless, of course, it's disturbed by some outside intervention. So what that's saying is, say you have a reaction between two things, you finally get it to equilibrium, it's going to stay there, unless you decide to get involved in adding new things like changing the concentration. That will mess it up and it will not be in equilibrium anymore, and it will have to start going through its process again of balancing out. Or you add more temperature, that's going to change the equilibrium. You add pressure if it's like gases or things that are dissolved in water. So there's certain ways you can mess up the equilibrium and it will have to start again trying to balance itself out. But if you don't, if there's no outside intervention, the equilibrium will remain. And so this is a law in our observable creation, or our observable chemistry world. So once we realize that, then of course we can understand it a little bit more, start calculating, and how we learn to calculate it and then how to use it. Okay, so that leads us to the next one, which is what we call the equilibrium constant. And I'm using this other book to kind of prop my book up a little bit because it's towards the end and there's barely any pages on this side. In fact, I probably have to splice in some extra pages because I'm running low here. Okay, so the equilibrium constant. So what is that? So what that is it tells us all we need to know about how much reactant and how much product exist at the point of equilibrium. So like we were saying before, if you start a reaction, in the end, you might start with this much of a product. So whenever they do a generic writing of an equation, you've seen this before, little a is your coefficient. So it's going to be the big number, right? Coefficient. Yes, is that the big number? Yeah, I think that's the big number. Every now and then I get my terminology, but let's just say the big number so I say it correctly, but I think it's coefficient. But your little a would be the big number. So if you had like 2 NO2, the big number, and then your A is your first substance. So you got the number and your substance plus the number and your second substance. And then there's your little arrow of moving through chemical reaction, creating the equilibrium there. Big number, with the first product, and big number with the second product. So let's say if we start out with this guy, and say we have a whole bunch of it, and we add a whole bunch of it to this guy. In the end, when it's going through its chemical reaction, it starts forming products. In the end, some of this is used up in the making of the products. So you don't have the same amount that you started with, which makes perfect sense. So I put this together and this together, I form this and this. I'm not going to have the same amount of this or that left over. And so it tells us what we need to know about how much reactants and how much of the products exist, how much of this exists once it reaches equilibrium. And so what we have to do is learn to calculate that. So this is a generic equation that's helping us take this generic equation for the equilibrium constant, taking this regular generic formula and sticking it in here so you could understand how the formula works, okay? So I'm trying to get this a little bit closer. I'll mess up my camera here, but it's kind of hard to see there. But this K is going to be the equilibrium constant. And it's going to be equal to, now if you remember, A and B are going to be your reactants and your C and D are going to be your products. So I've got A and B here on the bottom. My little a is the number, which would be my big number in my formula. And EQ is going to be the signal of how much you have at the time of equilibrium, how much product and how much reactant exists at the time of chemical equilibrium. So you got to put this EQ because that's symbolizing not how much I had when I first started, but how much I had at the point of equilibrium. So I've got my two reactants here on the bottom, and my little a would be the number of that, my little b would be the number before this particular substance. And then over top of that, I'd have my two reactants in the same manner. Big C would be the reactant itself plus the number in front of it, and D with the number in front of it. Okay, so we have to remember a couple things. The brackets indicate concentration. So we're saying concentration of A, which would be in a mole situation, molarity, and molality, yes, molarity. Let's see, moles per liter. Okay, so brackets are concentration, and then the little EQ is symbolizing once equilibrium is reached. How much do we have once it's reached? And that will help you calculate the constant, so the equilibrium constant. So as an example, they give us, okay, so they have N2 in its gas form, okay, and then O2 in its gas form and 2NO in its gas form. So they say in this formula, you have this, it goes through its reaction, it finally reaches equilibrium, and when it does reach equilibrium, these are the amounts that we have once it reaches equilibrium. So we have 0.354 M, big M, 0.124 big M, for this guy, and 4.15 big M for this. So these are the concentrations of what we have left, or what we have when equilibrium is reached. So therefore, then all I got to do is add it to the equation. So I've got the K, because I'm trying to find the equilibrium constant. What constant between this amount is there? So I take on the two on the bottom are going to be my two reactants, the first of the problem, right? So I've got my first two reactants. I got N2 goes down there, and then I got O2 goes down there. And they both don't have a number in front of them, so they don't have to have any number outside of their bracket. Okay, and then but NO has the big 2 here. So NO, and then the 2 goes over here from his original from the original equation. So what does that look like? So all that looks like is take the numbers, and this NO2 is 4.15 big M with 2 out on the outside. Okay, this is me taking this formula and filling it in with the actual numbers now. Okay, and then N2, we found out N2 was 0.35 M, so 0.35 M. No big number to multiply it by or square it by or whatever. And then O2 was 0.124 M, 0.124 M. And so there you go. All you have all your numbers. All you do is use your calculator to calculate this. Don't forget that that 2 is there. And when you divide up after you do your multiplication and squaring, then you have 465. Now, do notice that the M is crossed out because there's going to be 2. See how the number 2 is? That means there's going to be 2 sets of M there. And there's one set of M here, one set of M here. So these 2 M on the bottom will cross out these 2 M on the top. This is not always the case. Sometimes with the numbers, depending on what your formula entails, you won't be able to cross out all your m's. And if you don't, then you're going to have to actually add a unit to this. Sometimes if there's one left over, it might be 1 over m. Like say for instance, when you do this one, and I'm not going to calculate this one for you. I thought you could try this one and the answer's in the book after, let me see which page that is, after you try it first though, okay? I want you to try it so you're practicing along, and it's pretty easy. You're just pretty much typing in the numbers, but the answer will be on page 531. Okay, so you have this equation, and it's very easy. So you have, this is how much left at equilibrium. This is how much we have of this guy, how much we have of this guy, how much we have of this guy, how much we have of that. So here's your two reactants, here's your two products. You take this formula, you got your two reactants on the bottom. Don't forget the little number outside is this big number here in the front. So if I put in A, I would put this 0.80m and then brackets, and then I would put for that number, I'd have to put a number 4 out there. Okay, so this will eventually be bracketed in with a number 4, so we don't forget. Okay, so you'd put A and B on the bottom with both of their big numbers, and then above it you'd put the two products with both of their numbers. But what you'll notice here is by the time you're using a number 4, a number 7, a number 4, and a number 6, when you're trying to cross out all your M's to make sure that they even out, whether you would need them or not as a unit, there will be 1 M left over. So because there's going to be 1 M left over, it has to be added to the answer. So your answer will have a unit in it, which will be 1 over M, because 1 M will be left over. All right, so practice that one and see if you get it. And that's just an easy way of figuring out what your equilibrium constant is. Once your chemical reaction gets to equilibrium, how much of each one of the substances do you have, okay? All right, then once you continue on with calculating the equilibrium constant, there's some rules about it, okay? And I just tried to make these as simple as possible so they'd be easy to memorize, because some of this stuff, it's like 5 pages long of instruction, and it sums down to like, okay, well, let's just put this in easiest points here because there's so much information. So here are some of the main things we have to think about when it comes to the equilibrium constant. First of all, once you calculate it, which is what I'm talking about, the equilibrium constant, which we just did, we have to know, what does that mean? Like, what is K? I mean, I understand that's the equilibrium constant, but what does it mean? Like, and what do you use it for? So what does it mean and how do you use it? So that's the first thing we have to take a look at. We have to understand what it means and how we use it. And we do also have to note that it never changes as long as the temperature doesn't change. And so if you don't change the temperature, no matter what, no matter the initial concentrations of the substance or whatever, once you get your K, your constant that you solved for, it will not change if the temperature of the reaction is always the same. So no matter what your initial concentrations are going to be. So that's good. So once we figure out how to calculate it, like we just did, then we figure out what does that mean, how do we use it, and we know that it won't change as long as we don't change something like the temperature that the reaction is taking place in. So the other thing we can note about it is that it can be used as a gauge to tell us the relative concentrations of the reactions and products when the reaction reaches equilibrium. So what that means is once we do this calculation, we can look at it, just simply look at it, and we can figure out what happened in the reaction, whether you have in the end more products or if it's going the opposite way and it's more leaning towards the reactant, whether you have more reactants and or if it balances out. So it can become this gauge to us, just calculating that, that chemical equilibrium constant. All right, so here's the thing. If your K is very large, so if you end up calculating it and then your number for K is very large, and that would mean that it has a lot of products and only a few reactants when it reaches that point, okay? And so we would say with that it's weighed toward the product side. So just think of once you do the calculation, you look at the K number and you go, oh, It's a large number. That means that the reactants were used up and you end up having more products. Even though it's still, you got that going back and forth thing once you hit that line, it ends up having more products and less of the reactant left to go back and forth with. And so it's weighed toward the product side. And the way you symbolize that is to create the one-way arrow. And this is what we normally look at. Okay, when we do reactions, we're always used to just that one arrow. And so, but that one arrow is an indicator to us, late now that we understand this concept, that there were more products in the end and fewer reactants in this process when it was trying to make its way to equilibrium. All right, if the K is small, if it's a small number, then what you know is there's a lot of reactants and few products were formed. And so you have fewer products, more reactants. And so you would say this is weighed toward the reactant side. And that's when that particular arrow would become the arrow of use for this particular situation. And so when you see that, it's weighed towards the product side. If you see this, it's weighed towards the reactant side. And then if you see that doubling, that double guy, then you realize it's a balance between reactant side and product side, like we're seeing with chemical equilibrium. Okay, so if the K is close to 1, so this one, K, super big number, or if it's a big number, weighed to the product side. Small number, weighed to the reactant side. But close to the number 1, if your K is close to the number 1, there will be approximately equal amounts of reactants and products. And so it's going to be equaled out in a sense, and then you have your equilibrium sign there. And so this is a short version of trying to understand how this chemical chemical equilibrium constant can become a gauge. It can become a gauge. So you calculate it, you look at it and go, oh, okay, man, the number for K is close to 1, so I've got this sign going on. Oh no, my K is such a large number. My arrow is going this way, and it's one way because it's weighed more to the product side. Now, this one-way arrow does not mean it's really not doing this, because we have already said it is doing this, but the amount of the back and forth is so unnoticeable because most of the product has reacted, or most of the reactants have reacted and created a whole bunch of products. So it's weighed heavy on the product side versus the reactant side. Okay, so this, for a chemist, would give us more understanding with, oh, I see that. Oh, okay, I know what that means. More products, less reactants.